Sharing or
PPT அனுப்பிச்சிட்டாருங்க மேம்.
okay.
நான் தான் ஷேர் பண்ணேன்.
Okay, right. Then you have to coordinate.
Okay.
Good afternoon, Professor. Good afternoon. Good morning to you.
Good afternoon.
Hi, Deepti. Hello. Good morning.
Good morning. Good afternoon.
Good afternoon. Yes. Welcome, sir. Professor Kothari, sir. Good afternoon.
Good afternoon.
Ganesh, participants join lunch.
மேம் இன்னும் 1 minute இருக்குங்க மேம்.
Dr. Murugan, the voice is slightly not very clear.
Oh, it's not reaching you?
Sometimes the voice is not very clear. There seems to be some background noise. I'm not sure.
Sir, now
Ganeshan, Sajesh கேட்டுக்கங்க. என்னப்பா ஆல் மேல தான் மைக் ஆன்ல இருக்க போகுது.
ஆமா மேம் அது
You no, you have muted all mic. Professor, is it okay now? You have to unmute your mic and talk.
Hello.
Yes. Professor Potluri, sir, you have to unmute. If you have to talk, then you have to unmute. Because
Yeah.
yes, yeah.
Rest of the time, you can keep it mute.
You hear me, madam? Hello? Murugan, can you hear me now?
Yes, sir. Your voice
that's
is
good.
clear, sir.
Oh, excellent.
So I'm Ganesh and not Murugan.
Oh, okay, sorry.
Ganesh,
Ma'am?
voice echo ஆகுதுனாரு Professor Potluri. இப்போ
ஓகே ஆயிடுச்சுங்க மேம்.
okay.
அது எல்லாரும்
Madam,
மைக்
it's
மியூட்
better now.
பண்ணாம இருந்தாங்க.
It's better? Okay.
Yeah, it's better. Yeah, I think probably in the control room if you mute.
Yeah. The control room, they have to mute all the mics.
Yeah.
You can start, Ganesh. Who is the session chair? Prasad sir is chair. Co-chair?
Dr. Ganeshan.
Huh?
Dr. Ganeshan.
Okay, Dr. Ganeshan. But echo வருதுங்களே. Your voice is not Murugan.
Hello, ma'am.
Your voice is echoing, Murugan. Where are you now? You are talking from your home only, no?
Yes, madam. Yes.
Some vibration is coming.
அவர் மவுத் கட்ட வச்சு ஸ்பீக்கர் பேசுவார் மேம்.
இல்ல நீ இங்க செக் பண்ண சொல்லு சஜேஷ்.
மேம் சொல்லுங்க மேம்.
ஏதோ வைப்ரேஷன் ஆட்ட வருது.
இல்ல மேம் அவரு இப்ப எதுவும் ப்ராப்ளம் இல்லைங்க மேம். நீங்க பேசுறது எனக்கு தெளிவா தான் கேக்குது.
Murugan, can you talk now?
மேம் அது அவரோட வெளியே பாத்தீங்கன்னா நான் இந்த காத்து அடிக்குதுல மேம். சோ அந்த நாய்ச்சு மேம்.
காத்து அவர் வீட்டுக்குள்ளே தானே உட்காந்துருக்காரு.
தெரியலங்க அவர் எங்க இருக்கான்னு கேட்டாதான் வந்து.
முருகன் சார், நீங்க தான் இப்ப செஷன் சேரா இல்லையே?
நான் கிடையாது, கணேசன் தான்.
கணேஷ் ஓகே. சம் யுவர் வாய்ஸ் எது ஆகுது.
இப்போ ஓகேங்களா?
தெரியல, உனக்கும் அப்படிதான் கேக்குதா கணேஷ்?
எக்கோ அடிக்குதுங்க மேம்.
நவ்
இப்போ ஓகே.
ஓகே.
அவரு மவுத் கிட்ட வச்சு அந்த ஸ்பீக்கர் வச்சு பேசிப்பாரு.
Maybe you can start at 2:05 or something.
மேம் இன்னும் 1 minute ஸ்டார்ட் பண்ணிடலாங்க மேம்.
Let them all join. Speakers are there, no? Kothari sir and Deepthi ma'am. Okay.
இருக்காங்க மேம்.
Okay. Raja, ASM Raja, you are there from morning. Good. Dr. Prakash Kumar, Hema Malini.
Can we start, ma'am?
Yeah.
Good afternoon to one and all present here. Welcome back to Plenary Session 6. It's my pleasure to introduce our today's session, Dr. Prasad Potluri. Prasad Potluri is a professor of robotics and textile composite in Department of Materials and the director of research at Northwest Composite Center. With a PhD in applied robotics, he started his academic career at UMIST in 1994 and worked at the interface of textiles, composites, and robotics. Prasad Potluri has extensive industrial collaborations and has received funding over pound of 14 million from a variety of sources, various sources of including TSB, DSTL, and US Air Force. He developed a number of novel machineries for 3D weaving, braiding, robotics, fiber placements, and complex weaves. He is a principal investigator for EPSRC Center for Innovative Manufacturing in Composites. Prasad Potluri has published over 150 papers in peer-reviewed journals and conference proceedings in the area of textile composites and mechanics of fiber assembly. He is a member of the Material Technical Committee and is also one of the editorial board of Textile Research Journal of Industrial Textiles and Advanced Manufacturing. Prasad sir, we are welcoming you for this session chair for this session. The theme of the session is enzymatic finishing and medical textiles.
Thank you very much, Dr. Ganeshan. First of all, good afternoon to everyone, and happy Ganesh Chaturthi.
Thanks, sir.
So, the first speaker is Professor Vijay Kothari. It's my pleasure to introduce Professor Kothari, who has been a distinguished alumni of IIT Delhi, UMIST, and Leeds Universities, three major centers known for textiles. Professor Kothari has a long, distinguished career and needs no great lengthy introduction, really. He worked in industry for Gwalior Rayon for a short period before embarking on almost 5 decades of academic career in textiles. He also served as an associate dean at IIT Delhi during 1991 to 95, and he published extensively over 200 journal papers, 100 conference papers, 80 trade papers, 18 books and book chapters. I think his list is endless. He also received many distinguished awards, including honorary fellowships of the Textile Institute, the Textile Association, Institution of Engineers, and also received IIT Delhi's prestigious silver medal. Today, Professor Kothari will talk about issues around medical textiles. Sir, Professor Kothari, if you can spend about 30 minutes on the talk and leave about 10 minutes for questions and discussion. So the questions will pop up in chat box, and I will read out one by one. And if you can address them, that will be great. Okay, sir, you can start now.
Thank you, Prashad. It's a great pleasure to be talking to you on the occasion of Ganesh Chaturthi on the medical textile issue, which is whether to use disposable non-wovens or the durable woven fabrics for the medical clothing. So can I really have the presentation, please, before we move on to the
You have to share the presentation. We share it.
presentation with you.
Yeah. It's
Yeah, it's coming up.
Sir, can you start, sir?
Yeah, I can start now. Hello.
Hello.
We're going to talk about the medical clothing in general. Although the medical textiles are used in a wide variety of applications, including hygiene and healthcare applications, implantable medical textiles, plantable medical textiles, extracorporeal medical textiles, and so on and so forth. So the focus of this particular talk is basically going to be on the medical clothing only, although there are a large number of medical textiles in general. So can we really start with the issues of the medical textiles in the next slide? If we have the next slide, please. Hello, the market demand for the fabrics used for the gowns, drapes, masks, etc. has increased considerably due to the hygiene considerations and the increased sort of number of infectious diseases. The gowns and drapes are normally made from the barrier sheet materials, which could be either woven or the non-woven materials, which are supposed to provide a barrier to the microorganisms, the particulate matter, and the fluids. So the purpose is to sort of protect the person who is wearing these materials or who are using these materials from the microorganisms, particulate materials, and fluids, which could really be infectious. Now, if we really look at, hello, next slide.
Yes, sir.
If we really look at the important trends in the infection control, I think the slide is okay. Yeah, this is the slide we are really referring to. The infection control trends, if we really start looking at them, there is an increased awareness of the infection prevention among the healthcare professionals. There is a growing sort of concern about the hospital-acquired infections and the infectious diseases. Then there is a reassessment of clinical practices for better health outcomes or patient outcomes. And the market is now really moving from the reusable to the disposable medical clothing, but we need to really address the type of sort of concerns which we have for the disposable clothing before we really sort of go further. So if we go to the next slide, the main medical clothing we could really talk about are the gowns, the drapes, the mask and the respirators, the coveralls which are being used as a PPEs in the current pandemic situations. And there are other medical clothing. We can really talk about the head covers, the foot covers, etc. But mainly we will be concerned about the gowns and the drapes in this particular presentation. So if we really look at, yeah, next slide, about the medical gowns. Okay, we just focus on this particular slide regarding the medical gowns. So the gowns are basically the examples of the personal protective equipment which is used in the health care settings. They are used to protect the wearer from the sort of spread of the from the sort of microorganisms, particle matter, and the sort of fluids. And these sort of could really be quite sort of infectious. So the sort of protection of the people who are using these gowns from both the fluid as well as solid materials is necessary in order to control the uh, sort of infections in the medical settings. So if we really go to the next slide, we are really looking at the important sort of characteristics which we need in the case of medical gowns. The first characteristic is that the fabric should be effective barrier between the source of infection and the user of the gown. The second important property is that there should be adequate air permeability. That is, the air permeability should be optimized. The fluid we should really have a fabric which is breathable in nature, which could allow the water vapor permeability in adequate measures. The fabric should also have good strength. Then we should really have the fabric which should really be sterilizable. We should be able to sterilize the fabric, and it should also be not too expensive. So we should really be looking at these characteristics in order to really look for the clothing for the medical gowns. If we go to the next slide, yeah, then we are really looking at the barrier property, and a good barrier fabric basically refers to the specially designed fabric having the capability of resisting the movement of microorganisms, the particulate matters, and the fluids, but should really be water vapor permeable so that the person who is wearing this clothing could really be comfortable as such. So we really can look at some of the things in which this barrier properties could really be imparted. In the next slide, we have listed down some of the methods which could really be used for imparting the effective barrier characteristics. Some of these are increasing the basic weight of the clothing, uh, sort of doing the coating or using the sort of breathable films. We could really be looking at the low denier fibers, use of the melt blown layers in the fabrics, the bicomponent fibers could be used. We could really be laminating the microporous films or the monolithic films with the textile materials, and we could also be providing the barrier to an extent through the
Sir, so can you unmute and talk?
uh, uh, or we could really be looking at the plasma treatment. So there are many ways in which the barrier characteristics of the fabric could really be either imparted or improved. If we really then look at the type of fabrics which are used for gowns, before that, we would also like to look at this stage the surgical drapes. So let's look at the next slide. A barrier sheet material which is used in the to implant the or provide the barrier between the microorganisms, the particulate matter, and the fluids in the sort of surgery settings or in the sort of rooms in which the surgery is carried out is referred to as the surgical drape. And these fabrics should also have certain characteristics which are listed in the next slide. The characteristics we are again looking at is okay, we'll look at some examples of the barrier materials which are used as a drapes. Basically, they would really be of many sizes and types. There would be certain openings which would be used for sort of purpose of operations, but the rest of the fabric would really be covering the parts which are not really being operated. So if we really look at the next slide, you could really see that only certain part of the body has been kept accessible to the doctors who are operating or the surgeons who are really performing the operations. The remaining things have been sort of covered with the drapes of various types and sizes. So if we really look at the characteristics we are really looking at in the drapes, they are the once again the excellent barrier characteristics, should really have good strength, should really be low linting, so the lint should not really be coming out, should be soft and drapable, should really have good adhesion to the skin, low flammability, good absorbency, and in general, in most of the operating situations, most of the drapes are required to be non-breathable as well. So if we really look at the next slide, we could really see the type of materials which are being used for the gowns and drapes. Both woven fabrics and the non-woven fabrics are used. The woven fabrics are referred to as a sort of reusable materials. Next slide, if you can look at. Hello. Can we change the slide? Yeah. Okay. So the reusable materials normally used as gowns and drapes are basically the woven fabrics. These fabrics could be made from cotton, polyester, or polyester cotton blends, whereas the non-woven fabrics which are used as a disposable medical clothing uh, are basically either the sort of different types of non-woven fabrics, or most of the it really tends to be SMS, that is some composites of spun bond, melt blown, and the spun bond material, or a melt blown sort of laminate with the microporous films or a monolithic film, which would allow the to provide the very extremely good barrier characteristics. So both reusable materials as well as the sort of disposable materials or the single-use materials are used in hospital settings for the purpose of the gowns and drapes. If we look at the next slide, we could really see example of a woven fabric and an example of a non-woven fabric, that is SMS fabric. The pore size in case of woven fabric tends to be large. So if the woven structures are used without special sort of processes or coatings, etc., they may really fail to perform as an effective barrier. Whereas non-woven fabrics, especially say SMS, has reasonably good barrier characteristics, but not as good as the uh, laminated structures or the sort of a composite of a non-woven structure and the microporous films. So we would really be looking at some of the advantages or the uh, good points regarding the woven fabrics and their use in the medical setting, and some of the major disadvantages of these fabrics. So if we really look at the next slide, we are really looking at the advantages, which really are basically the woven structures tends to be soft, drapable, and supple, tends to be absorbent in nature. They are biocompatible and could also be autoclaved at high temperatures. So no special autoclaving or sterilization techniques would really be needed. Whereas in the disadvantage side, the barrier properties are not extremely good, and we might really need to have certain treatments, coatings, etc., in order to improve the barrier characteristics of these materials. And these fabrics also tend to be lint generating, which is a major disadvantage of these fabrics. If we really look at the next slide, which really talks about the advantages of the uh, sort of a SMS fabric, which is widely used in both the gowns and the drapes. The one of the advantages is that it has lower unit cost in comparison to the woven structure or the reusable structures. Has reasonable fluid resistance, are breathable in nature, and have low linting characteristics. But the disadvantage of this particular material is that they are not non-absorbent, sort of really have limited fluid resistance, and really require low temperature methods for the sterilization. So there are disadvantages. Some of these advantages like uh, uh, low absorbance and sort of barrier characteristics which really need to be improved could really be done by the use of composites, composites of films, spatial films, and non really tries to compare the three major categories of the materials which could really be considered for the gowns and drapes. The, if we really look at the next slide, then we can really see that the disadvantages of both the woven structures as well as the SMS structure has been overcome to a very large extent by the use of the sort of composite materials of films and nonwovens. And the barrier characteristics of these fabrics are extremely good. They are also going to really be uh, good to uh, feel, and also would really be useful in the very critical medical sort of operations. Uh, so we could really say that all types of materials are used. In each one, there is certain advantage and disadvantage. If you really talk about the materials with the laminated films, etc., the breathability is limited, but the barrier characteristics are extremely good and would protect the user from the microorganisms, uh, the fluids, or even the particulate materials which could be infectious in nature. So we would really be looking at these materials for the use. There are various types of standards which have been developed internationally for the barrier materials. A list of these standards is given in the next slide. Uh, in each of these standards, there would be levels 1 to 4, or there would be different levels of protection or the barrier which will be given by the product, and the type of product characteristics would really be changed depending on the level of protection which is required in a particular sort of a medical setting for protection against the infectious fluids and solids. So we can really move to the next slide. We really have the major advantages of the disposable materials listed in this particular slide. Since most of these disposable materials are non-woven in nature, so the production process is fast and easy. The It is also easier to engineer and modify the properties. The type of changes which could really be done in either sort of a density of the material, or the sort of weight of the material, or the fineness of the filaments could more easily achieved in the non-woven process. The other advantage is that the materials are going to be factory sterilized, single-use products. So it becomes much easier to control the sterilization process, and therefore it will give much more confidence to the medical workers with these materials. The people who are going to be using these would also feel fresh and clean every time they use these materials, because they would really be using them once only. And then the unit cost is also lower of these disposable materials which are used in gowns and drapes. So the cost of single unit obviously would be lower. But if we really look at on the negative side of using these disposable materials, then what we really have listed in the next slide are some of the disadvantages. These disadvantages really look at the high waste they generate, because after each use of the gown or the drape, we have to throw away the material. Whereas in the case of the reusable materials, the same material could really be sort of washed and sort of sterilized again, and therefore the disposable materials tends to have higher overall cost for the user. The main disadvantage is it really generates a lot of waste, which has to be sort of suitably disposed of. Uh, Incineration is obviously recommended for the purpose of disposal, and this also really is uh, uh, sort of limited, and not all medical clothings are disposed of as recommended. Therefore, they really create environmental issues and health hazards for the people who handle them, and also who could really be coming in contact with the type of contaminated materials. So one is obviously the environmental concerns are very serious in nature. The amount of really waste being generated is very large. In the current pandemic, where the overalls are being used by the medical professionals, we are really generating large quantum of medical waste. Even in the surgical environment, if in all surgical procedures they start using disposable materials, the waste generated would really be extremely high. So the environmental issues, unless they could really be adequately addressed, could really not justify the use of disposable materials in all sort of situations. So if we really look at the overall important sort of observations regarding the medical clothing in the next slide, what we really are looking at is that the trend is obviously towards using the disposable clothing in hospitals because of the higher sort of emphasis on the sort of protection. Then obviously there is a higher sort of concern regarding the hospital acquired infections, and therefore the sort of trend is towards using more and more disposable non-wovens for the medical clothing. SMS material, which is widely used presently, uh, really provides the good or reasonable barrier characteristics, but they may not be suitable or may not be adequate in the critical surgical um, settings or surgical applications. So what we are really looking at is obviously if you can use the reinforced non-woven, which will be providing the best barrier characteristics, and for most surgeries, they would really be extremely useful. However, the cost obviously of such materials would really go up, and therefore it may not also be justified in uh, many cases where the disposable materials are being used. The next important observation is that the proper disposal of the disposable medical clothing is essential and is a matter of great concern at the present. The way the clothing ends up being handled at the end of use and the way it is disposed of is not really adequate at present moment, and is a matter of serious environmental concern. The next point we are really listing is that the cost of using disposable clothing is obviously higher and may not really be justified in all surgical procedures or in all sort of uh, 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 applications. So one has to really balance between the sort of environmental issues which are being raised, and these are true with reference to the other medical clothing which are being used at present also, and the use of the reusable material and proper sterilization could really be one of the answer which could really be useful for certain surgical procedures as well. So these were some of the observations I had regarding the medical clothing, and I hope I've been able to complete it in the time which was allotted to me, and we can then take up some questions at this stage. Thank you very much.
Thank you, sir. Perfect timing. Thank you.
Yeah, any questions that has been raised as such?
Yeah, sure. I have one to here, and people continue to type in the chat box so I can present it to Professor Kotari. Somebody is asking, because PPE and face masks are produced in large volume nowadays, what are the most effective ways to dispose them in India?
I think what we have to really look at is who is using it. If it is for the surgeons or the people who are in directly contact with the people who have, say, viruses or the COVID as such, then obviously a disposable non-woven material which could really provide adequate barrier property would really be best.
Okay.
Hello.
I mean, do hospitals have adequate collection facilities?
Yeah,
Is my clarification.
they have incineration facilities, provided these medical hospitals who are handling these materials really dispose of carefully. Unfortunately, in Indian hospitals, we have all types of hospitals. Some of them are really good, but there are large number of hospitals where adequate cares are not being taken, and even these PPEs or the medical waste which is being generated in hospitals find way in the dumps, and
Oh,
obviously
that's unfortunate.
manually by people who sort of try to dispose them of, and therefore it is a serious environmental concern at present, as well as, although the recommendations are very clear, but the recommendation or the use of these recommendations would really uh, would require certain costs of really packing these materials properly, disposing it of, sending it to the incineration plant, and then properly sort of disposing of the waste. It is a very, very serious matter. And what is being said that you are using almost 6 lakh PPEs at present per day. Now, obviously, I would really imagine that at least 4 lakh PPEs would really finding their ways in the sort of waste dumps, which is extremely concerned. And people are aware of it. It's not that people are not aware of it, but I think they are not really able to do much. So maybe, hopefully, things will improve in time to come.
Uh, I think the government has to be strict about disposal with hospitals, I believe, because they collect lakhs of rupees per patient. And why can't they spend few rupees for careful disposal?
Not all hospitals really collect lakhs of rupees per patient. We are talking about some of the good private hospitals. They have good disposal sort of practices also. But large number of hospitals, including the government hospitals, which really treat the patient free of cost, do not really have adequate sort of facilities for safe disposal. This is the unfortunate situation. Government has regulations. Say, it's not the lack of regulation, it's the lack of implementation. That is, the problem with us is the implementation is really an issue. And in this particular pandemic type of situation, implementation really becomes even worse.
Yeah, thank you. There are a few more questions from audience. I'll read very quickly. Are there any specific Indian standards for surgical clothing?
Yeah, there are sort of what is known as, we developed some what is known as emergency standards. So BIS has developed emergency standards. Unfortunately, these standards do not really have different levels. So all sort of PPEs which are being worn are really resistant to the blood penetration, as if the people who are wearing the PPEs are going to be operating on people. So the type of sort of protection levels which are being specified as a part of those are really fairly bad. They are impermeable. They are basically laminates of the plastic films and the non-woven, which is the spun-bond material. So unfortunately, in the short period of time, in the last 2-3 months, the standard was developed, which is only meant for emergency use. The BIS is on the job to develop the proper standard. But meanwhile, we can use the international standard. There's no sort of bar on us using the international standard. So if you want to produce good barrier properties, at the same time, keeping in mind the comfort levels and the use of this material in a particular sort of situation, then obviously it will be good. So instead of using BIS standard, if we can use some standard which is of international level, but which is of a different level depending on the severity of the protection or the barrier which is required in a particular situation, would be a better option for me as far as I'm concerned.
And now somebody is asking about the possible role of milkweed in antimicrobial properties of these medical textiles.
We can use all sorts of what is known as the different materials which are inherently antimicrobial or whatever you say. But this virus is not this is not a bacteria. So the virus is much smaller in size, and we really need to look at the type of protection which we require for the persons who are wearing it. So to my mind, if the virus could really be washed away with the soap and water, then the best thing for them to do is to cover the mouth, the nose, and the eyes using the face shield. And the remaining things, they should really sort of emphasize on washing the hands and taking the bath after sort of being in contact or in the medical situation. And obviously that would really give them better protection than the way these PPEs are currently being used. But this is a personal view. Maybe some people agree with this, but many people don't agree because WHO specifies something else.
Okay, couple of very quick questions here. What is the cost difference between disposable and reusable PPE?
At least 1 to 4 times, probably. The cost per use would really be 1/4 for the disposable, but the cost if the PPE which is being used at least 3-4 times would be maybe sort of quite low, because this will get used many times.
Yeah, I mean that answers several questions flashing as to how many times you can reuse and Yeah, so that clarifies. Sir, I have one quick question myself. Is there any possibility to develop a reusable non-wovens? So they're cheap, but you can also reuse them maybe 2 or 3 times rather than single use.
There is a possibility. I think this could really be done. Even the woven structures have been developed by many companies in India, which they claim that they could be used many times. Only thing is proper sterilization would have to be kept in mind before using them. Unfortunately, even the non-woven PPEs being used at present in the current situations are not really being properly sterilized. So one can really look at the situation which is not really good for the medical professionals, which are basically using coveralls. The people who are using it in the operation theater settings, they are okay. But those PPEs or the drapes or gowns have really been used for very long time in the operation theaters, and they are being taken care of adequately. The PPEs in the form of coveralls and the coveralls which are being used are really very badly designed. Then they are not really keeping in mind the protection level which is required and the comfort level which is necessary for the people who are working in the high temperature environments. These were some of the observations I had regarding the medical clothing.
Yeah, thank you, Professor Kotai. There are lots of questions flashing up, but in view of time, we'll draw this talk to a conclusion. So we need to move on to the next talk. Thank you very much.
Thanks a lot for having me here. Thanks.
Thank you. Our next speaker is Professor Deepthi Gupta. Professor Deepthi Gupta is a textile chemist and currently a professor at Department of Textiles and Fiber Engineering at IIT Delhi. She has over 3 decades of academic experience, and she has done pioneering work on natural and sustainable materials around natural dyes, eco-friendly finishes. Currently, she's working on developing multifunctional finishes for textiles based on silk saracen. Professor Gupta also works on anthropometry and garment sizing systems for Indian population, and she published a textbook and has gone into second edition as well through Elsevier. And she's very active with international agencies, for example, Korean National Standard Organization, ASTM, and she attended many international meetings to represent on these standards. More recently, Professor Gupta has been working in the area of functional clothing, such as mama pod related to infants, motion sensing garments, cycle protection clothing, and very pleased to say that her PPE designs are being manufactured by several companies, and it's a great contribution to the current pandemic at this stage. And she also does administrative roles in IIT Delhi, including Associate Dean and also President of BRCA. And she finds time to serve on boards of many companies and board of studies for several institutes. She's obviously a very active person. And Professor Gupta also finds time to take interest in literature, art, music, and she's deeply committed to cause of solid waste management and women empowerment. So I invite Professor Gupta to start the talk.
Thank you, Dr. Patli, for the nice introduction. Good afternoon. Chair, Dr. Thilagavati, Dr. Perasamy, and the tech team for giving me this opportunity to yet again be a part of the INDUTECH plenary session. My presentation, I'll just share the slide. Is it visible to you?
Yeah, you can see, but it's not full screen for some reason.
I'll just do it.
Yeah.
Yeah, all right. So the topic of today's presentation that I decided to talk about is immobilization of enzymes on textiles, and a brief introduction about how I developed interest in this area. So when I first was writing a review paper for IJFTR in 2011 on emerging technologies in the field of textile finishing, that's when I first encountered this technique, that is permanently attaching enzymes to textiles. And at that point of time, when one looked at literature, there wasn't enough information actually available. People had started talking about it, people had started working about it in chemical engineering and such fields. But in textiles in particular, there wasn't much. So I thought it was a very interesting topic, and we did think about initiating some work in that area at our lab. We started something and did some work on enzymatic coloration, but did not really, for some reasons, we were not able to go into this field. And then last year, 2019, I was invited to evaluate a PhD thesis of a student in the University of Lille, and she was registered in the University of Lille and University of Paris, wherein she has worked with worked on immobilization of enzymes for development of bioreactors. So it was a very interesting thing for me to see. And when I did start looking at her thesis and then subsequently at more literature, how much progress had happened in this field. And so I dug a little deeper, and I thought I'd share what I have learned with you today. So as we are aware that in textile processing, chemical processing industry is always under tremendous pressure for being one of the largest pollutants, whether it is the use of chemicals, whether it is the use of the amount of chemicals that go into the effluents, or whether it is the amount of energy that is used or the amount of water that is used. This industry is under tremendous pressure to really get its act right. And so over a period of time, if you look at the history of textile processing in the last 100 years or so, this is the main driving force, that is, how can we reduce the pollution load, how can we reduce energy consumption, and how can we reduce the pollution that goes into water bodies, etc. And increasingly we find, if you look at the history, that every time we have looked at enzymes as a possible solution, or biochemistry as a possible solution, as a substituent to catalyze the reactions that are normally carried out by very severe or very strong chemicals and chemical reactions. So it's not like use of enzymes is new. And a general interest in enzymes is because they are biodegradable proteins. Important thing is that rather than being synthetic, they are available from renewable sources. They operate under mild conditions, so the pH is near neutral. The temperatures are almost always mild because enzymes can be activated at extreme conditions, except when they are extreme enzymes. And one very important characteristic is their specificity. So in the sense when we use, so it's substrate specific, it only catalyzes the reaction or works on the substrate that we are looking at, and does not affect the bulk of the textile or the substrate. And of course, being catalysts, they accelerate the rate of reactions, and emissions are significantly reduced, and they're environment friendly and cost efficient. So cost efficient I have put in red because I'm going to talk about it a little later, because there's a bit of a controversy associated with the statement. Although all enzymologists claim that it is cost efficient, but enzymes are quite expensive. So they are derived from an organism, mostly some fungi that catalyze metabolic reactions in living organisms and or substrate conversions in various chemical reactions. And as we know, there are long linear chains of amino acids that fold to produce a 3D structure, and it is this property which is responsible for their catalytic activity. So just to take you through very quickly through the traditional applications of what enzymes we have been using traditionally. They have been used in what we may now call as the free state. That is, it is added to the bath and the reaction takes place. When you drain the bath, all the enzyme also goes away with the effluent into the effluent. So, yeah. So the history of enzyme applications in textiles started with desicing, which was around the beginning of the 20th century, the 1900s, as a matter of fact. And but when amylases were used to substitute the acid decycling processes, etc. And interestingly, from 1900s to 1970, the only application of enzymes in textile processing was restricted to decycling. So no more development happened. But from the 1980s onwards, there has been a huge push where almost all textile chemical processing operations attempts have been made to partially or fully substitute the use of a particular chemical with an enzyme. Some of them have been very successful, some of them have not, some of them have been commercialized, such as biopolishing of cotton became very popular during the 80s, and where we use cellulases for removing the surface fibers in cotton. Then a very important breakthrough came in the form of bioscouring. Nobody ever thought there was another way of scouring. And scouring requires very high temperatures and very high alkalinity in order to remove the waxes that are there on cotton fiber. And then we were able to substitute it with what is called as bioscouring, which is a very benign process based on pectinases and lactases, a combination of enzymes which perform more or less the same action that the clear boiling of cotton does. And then next phase, we have surface modification of synthetic and cutinases and lactases, etc. for surface modification. This has not been very popular, has been studied and reported in literature. Sometimes it's used, but not really taken off in a big way. More recently, in the last 10, 15 years, we have been able to accomplish bleaching of cotton also with the help of these enzymes. And of course, one very important operation where again catalysis are used, which is a peroxidase, to kill. It's called as a hydrogen peroxide kill. So to remove the leftover hydrogen peroxide in the bleaching bath, so that it does not interfere with the subsequent dyeing operations, we have used enzymes, and this is not commercially successful, but fairly well established now. And then further on, discoloration of effluents, for removal of dyes, and also in coloration of textiles. So a whole variety of, for example, enzymes have been used in textiles for various kind of operations. But at the end of the day, now with the sustainability and cost pressures, we find that enzymatic processes, though they have all the advantages, are actually very expensive, because the process of purification and extraction of enzymes is actually very energy and time intensive. So when you use an enzyme, it may not be very, it's very effective, but the cost of production of an enzyme is still very high. And therefore, the feeling was that if we could recover the enzyme, because it's a catalyst, and just throwing off all the catalyst, which is still active with the effluent, is not a good idea. So that kind of led to the process or thinking of, can be immobilized, the enzyme. So basically what it means is that can be attached, and rather than putting a free enzyme into the bar and then draining it out with the, when the process is over, can we possibly attach the enzyme to a substrate, and in this case the substrate could also be textile, and use it, reuse it time and again. And the requirement is that the support that you use or the substrate that you use has to be obviously different from what is the active substrate of the enzyme, and should not be similar to the products. So what an enzyme immobilization does is that it improves the stability. There is not so much denaturing happen. It stabilizes once it has been put on some support, and you can use it again. So as I'll show you some examples towards the end, you can use it for 10 times, 20 times the same enzyme. So it leads to tremendous amount of savings in cost. And this is a long time functionalization of support. It's just there on the support, and it reduces product process costs, and it allows the ability to stop the reaction at will. It's just, just remove the textile and the reaction stops. So it's very, very beautiful in that sense. And because textile, unlike the other substrates that are normally used for enzyme mobilization, they do not leave a residue. You can just remove the entire this thing. The challenge of the requirement is that we should have a good enough enzyme loading of about 20 to 70 milligrams of enzyme per gram of textile in order for it to act. And it should have a high relative activity. So relative activity means the activity with vis-a-vis the free enzyme. So almost 80% loss in activity is there. But when you consider it in terms of the number of uses for which the same, or the number of times or number of reactions that the same enzyme can be used to catalyze, it works out to be efficient. And so up to 20% minimum should be there. It should not get dissolved. It should be durably bonded. That's one of the biggest challenges in this entire technology. And of course, it should be reusable. When we talk about doing this, it's actually easier said than done, because enzymes really have no direct affinity with textiles. So how do we load them? And how do we load such this thing and then ensure that the loading is durable, it stays on, and the activity of the enzyme is also not lost as a function, or as due to the fact that it is now bound onto the text. So these are some of the issues that we will talk about in this presentation. So this just shows you the advantages of free versus violized enzymes. So all these things are possible in this case. However, there is a reduction in enzyme activity, understandable. There is a diffusional limitation. Can it access the substrate on which it has to act? And of course, there is the whole cost of support and the technique that is used for immobilization. The interest that is there in this field in general, not just textiles, but immobilization of enzymes, is actually a universal phenomenon. Chemical engineers are very actively working on this. Biotechnologists are very actively working in this area. And there's some 20,000 publications. Like I said, there is the field has exploded in the last 10 years since I first looked at this topic. There are 20,000 publications on this topic alone in the web of science in the last 15 years. So what are the elements of enzyme immobilization? When we say, of course, we need a support on which we will immobilize it. That's the first requirement. The second is, of course, we need an enzyme. What is the purpose of the enzyme? What is the nature of the enzyme? What is the type of carrier that you are using? What is the kind of reaction that you are catalyzing? All of this will determine what is the method or process of immobilization that we use for this purpose. So this is what we are going to talk about. That is, when we talk about supports that have been used for immobilization, textiles are one of the last ones to when chemical engineers discovered that textile can be a very good support. So it's a highly interdisciplinary field, by the way, and a lot of interactions are there between chemical engineers, textile people. Not so much work is happening, but mostly chemical engineering and biotechnology. So the easiest and the commonest supports that have been used are inorganic in nature. So you have glass beads, you have cellulose, packed cellulose columns, alumina, silica gel, hydrogels, the usual columns on which you can absorb it and then use it for a reactor, etc. Synthetic polymers have been used, polyacrylamide, oxidizing, etc. People are now increasingly, to make the process eco-friendly, they're using natural polymers such as gelatin, chitosan, cellulose, microcellulose, alginate, agarose, which are actually the shell, and inside you have the enzyme. So, or you can absorb them in some ways. Many kind of techniques have been used. And like I said, most recently, even the chemical engineers realized that textile fabrics are a very good substrate, and cotton, polyester, nylon, carbon, wool, all of them have been explored as possible substrates for this application. So textiles offer a lot of advantages in the sense that they're the biggest advantage vis-a-vis metals or other glass beads is that they're porous, and therefore if you are using it in a reactor, the kind of throughput etc. that is possible with this is very high. The high specific area, they're stable. Textiles are very long lasting. Of course, they're the cheapest. This is one big advantage as compared to using gold and platinum, etc. And they're resistant to mechanical force. They are biocompatible. Quite a few textiles are biocompatible, and they're flexible. So whenever you want to use in a particular shape, etc., they allow that kind of freedom. They're resistant to corrosion. So that's one advantage against metals. And like I said earlier, you can easily remove the catalyst as compared to, for example, if you were using pellets or if you were using beads. So after the reaction is over, you have to filter them out, you have to remove them, etc. In this case, just remove the textile sheet and it's much easier. So this is why the interest in textile as for immobilization purposes. So when first people in the textile field started using enzymes for immobilization, as is expected, what happened was that whatever we were familiar with, so what they did was that the enzymes we already knew, for example, cellulose for biopolishing, etc. These same enzymes were immobilized onto textiles and then used for the same operation. That is, now you had zirconium chloride activated pumice particles, which we anyway use for denim washing. Now these have been immobilized on that. So the purpose is the same, the system is the same, except instead of a free enzyme, now we are using a immobilized enzyme. So similarly, pectinases for bioscouring, we still use them. Now we immobilize them. Amylases for immobilized on glass beads to remove starch stains. Proteases on a cellulosic for shrink resist finishing of wool. Glucose oxidases, we are already using catalases for peroxide kiln, and so on. So this is the first stage where immobilization happened in the field of textile finishing, or textile processing, where the same enzymes as we knew earlier were immobilized and used for the same operation. But what I want to focus on in this presentation is not this. All this is known, but the kind of possibilities, the new possibilities, the transformational possibilities that now emerge as a result of this whole possibility of being able to mobilize enzymes is that the spectrum has opened up. There are many new kind of applications, such as medical textiles. You can actually have permanently antimicrobial textiles by putting antimicrobial enzyme on a textile. There are self-cleaning and self-healing textiles, automotive packaging textiles. If you want to make them antifungal or if you want to make them antimicrobial, you can just treat them with enzyme and it's permanent. One very, very exciting and new this thing is wastewater treatment for textile dye and peroxide removal. So you make them a part of the processor, the reactor. And then we're also using wearable biosensors now for all kinds of glucose, alcohol, etc., and bioreactors. So these are some of the newer applications that we have in this field, which can be there. And so it's like I said, it's not easy. There's a lot of complex chemistry and complex methods that have been used and reported in literature for enzyme immobilization. They can be characterized as first type of thing is chemical bonding between enzyme and support. So, which is the most commonly understood mechanism in textile processing, that you bound or bind a particular finish, it could be in any case, with the textile polymeric chain. So methods that have been adopted are adsorption, encapsulation, cross-linking, entrapment, and covalent bonding. All these methods have been used. The second technique that has been approach that has been used is modify the substrate. So like we said, there is no affinity between the substrate and the protein. So if you modify the substrate, create some additional functional groups on this, it can have, the enzyme can have affinity. So this is one approach which has been used. The second approach is to give some functionality or introduce some functional groups on enzyme. And then that can be this thing. So both can be used. You can have modify the substrate and you can modify the enzyme and then bring about functionality. I'll show you some examples. And now, very recently, again, we are moving towards, can we substitute these chemical methods with dry and cleaner methods? So we are looking at photoactive processes. We are looking at plasma as activators for enzyme immobilization. So if you look at the chemical methods, these are the common methods. That is adsorption, which is just by some ionic interactions or hydrophobic interactions. It will be held. Of course, this is temporary. You can encapsulate the enzyme, like we said, a core shell, where the enzyme over a period of time, the shell diffusibility is important so that it can act, it can diffuse out and act on the substrate. The cross-linked structures can be used, which helps to fix it. Entrapment in a sol gel matrix kind of thing. This is also being used. And finally, the most commonly and the most preferred method as far as textiles are concerned is covalent bonding. So physical adsorption, like I said, yeah, the physical, this thing, all kinds of enzymes have been immobilized on various kind of substrates, and it's possible. Where durability is not an issue, where it's a temporary kind of a thing, physical adsorption is absolutely possible. Encapsulation, people have tried and used nylon or polymeric membrane of nylon or cellulose nitrate to form micro or nano capsules. And you can control the loading, you can control the trigger using this. And this is one of the preferred methods of applying these special finishes. Cross-linking, we all know cross-linking, we use it extensively in textile processing. So cross-linking is interesting in the sense that the enzyme molecules cross-link with each other to form a network, and then they cross-link with the substrate also. So this is better than physical adsorption in terms of stability. But as we know, in case of all cross-linked 3D network structures, it makes the fabric brittle. So an enzyme activity may be impaired because of this cross-linking between molecules. techniques. However, this is one of the techniques which is used. And the next is entrapment. Entrapment is used extensively because hydrogels are an important and interesting way of applying any finish nowadays. So you can entrap the enzyme in hydrogel or microcapsules, and gel porosity can be controlled to prevent enzyme leakage, and gentle conditions are possible. And this, of course, suffers from mass transfer limitations as diffusion occurs inside the biocatalyst in addition to the thin layer of liquid trapping the enzyme. So there are pros and cons of each one of these methods. The most effective, let us say, or the most popular or preferred method is this last technique, which I'm going to spend the next few slides on, which is covalent bonding. So covalent bonding has many advantages. Of course, we always prefer it wherever we are looking for a durable finish. There's a strong linkage between the functional groups of textile and the amino acid groups, either amino acid or carboxylic acid groups of the enzyme, and there is no possibility of leaching into the medium in this case. However, the challenge is that it requires an active surface, and fibers, textile fabrics in general are non-reactive. So we may need to enzyme modify the fiber surface support or the enzyme or both, and accessibility of the active enzyme after this, because the orientation of an enzyme is important, can be an issue. So these are some of the points of research that people are working on. How can we fix an enzyme to the maximum extent, and how can we ensure that maximum activity is retained? And so these are some of the approaches. Very interesting work has been done in this area. You can modify the textile support. All types of methods have been used. First degree was chemical methods were used. Then now people are shifting biochemicals, such as enzymatic methods have been explored. And now the trend is towards moving towards the physical or dry methods. So substitute these chemicals basically to create some active functional groups on textile substrate. So traditional cross-linking agents have been used, like we do is recovery finish and any durable finish that we put. The same groups such as butadiene, cyanuric chloride, carbodiamide, etc. have been used to increase the functionality of the cross-linking agent and to increase the amount of loading of the enzyme. Biofunctional cross-linking agent, bifunctional, with double functionality, so that more number of bonds can be formed and more points of attachment are there. Diallyl, phthalate, cyclohexane, 1,4-dimethanol, divinyl ether kind of agents have been used. The other approach, as I mentioned earlier, is to modify the enzyme itself. So people have used all kinds of chemical methods or physical methods to impart additional reactive groups on the enzyme. And now in the physical methods, we have photocurable catalysts and active catalysts. Also, use of these physical methods for curing, etc. So, when we talk about functionalization of cellulosic supports, what we want to do is binding of any of these groups of the enzyme to cellulose is the objective. And because otherwise, for example, on cellulose, you only have hydroxyls. And hydroxyl groups and enzyme, there is not going to be much bonding. So there will be very weak interactions. If we want strong binding, then we have to have some kind of a cross-linking. So therefore, for which we need functionalization. So for cotton, for example, two approaches have been used. One is to introduce cation groups, amino groups on the surface of cotton so that they can bind with the carboxyl groups of the enzyme. Alternately, we can create cation groups on cotton which will bind with the amino groups of the enzyme. So both strategies have been adopted. And the third is activate the enzyme. All possible combinations can be used. So this is an example where if you see this cellulose has been modified with citric acid to create these additional carboxylic groups. So it is carboxylic group activated cotton with the help of treatment with citric acid. So that's the first preparation step for modifying the surface of the support, in this case cotton. And then this carbodiamide crosslinker is being used, and this activates the amino group of the lysozyme, so that when you treat it, you get a cellulose on which the carboxylic groups are there, to which the lysozyme enzyme has attached during the covalent bonding has taken place. The second option, like we said, is that you have this cellulose. On cellulose, you can put this amino groups now, right? With the silane amino group, you can modify it. And then again, you have lysozyme, in which the carboxylic groups have now been activated. The same cross-linking system is used, and you can have this kind of a system. So either we can have cationic groups on cellulose, or we can have anionic groups, and the corresponding complementary group of the enzyme can actually form a covalent bond. So these have been used. You can use these things so very successfully. However, I would like to mention that if you look at the detail kind of of the processes, they are extremely long drawn out processes, extremely complex. So as of now, not commercialized, but a proof of concept has been provided that this kind of chemistry is possible. And in this case, they were able to get very good bonding and very good activity of the enzyme. The second, if we are still working with cellulose, can be introduction of aldehyde groups. Again, we use the same kind of chemistry. It's very well established. In this case, for example, they have used sodium periodate to oxidize and create these dialdehyde cellulose, which in turn is capable of reacting with the enzymes. So this also shows you the same kind of thing, where sodium periodate oxidized enzyme or cellulose is there, oxycellulose, and when you combine it with this, the amino group reacts with the aldehyde, and you get a covalent bond here. You can use another oxidative agent also, and the same kind of chemistry follows. So various kind of enzymes have been used with various kind of substrates. This is as far as cotton alone was concerned. But if we look at the chemical modification of cotton, polyester, and nylon, it all have, so there are very few groups who are working, and most publications are by the same people mostly. And they have very interestingly shown how you can use a different, for example, on cotton, they have used cyanuric chloride as the reactive group. So cyanuric chloride, as you would recognize, is the group that is present in a lot of, is it time, Dr. Prasad? Okay, so please tell me when it is time. I can't hear you. So you can have this kind of cross-linking groups. And in this case, again, on polyamide, you add dialdehyde. On polyester, you add carbodiamide, etc. And you can get different kind of functionalities. And finally, so these were all chemical intensive processes. So now like I said, people are now trying to substitute part of the chemical functionality by use of, for example, in this case, they used monochromatic UV light of 222 nanometers to catalyze this reaction. So they had a photoactive cross-linking compound added to the mixture, and there is the enzyme, and there is polyester. Now, polyester itself is a very good absorbent for UV light. It gets activated, and there is one cleavage, and the photoactive cross-linker gets activated, an enzyme gets activated, and together they are able to form a nice cross-linked and covalently bonded structure on textile. So similarly, they modified the enzyme to do this. So I'm just coming to the end. And this is one very interesting, this is the thesis that I examined. Nikahush has actually kind of reached, used all this knowledge and understanding to create a system that is actually commercializable and actually works. So for example, so this is like a case study. She used carbon non-woven felt, decoated it with P dot PSS to make it conductive, and then treated this coating with plasma to functionalize the surface of the coating. On this functionalized surface, glucose oxidase enzyme was durably immobilized, and this was then they tested its efficiency as a bioreactor and found very good activity. Now, then further she extended the study to also use a crosslinker. And now in this case, the crosslinker used was a naturally occurring crosslinker instead of the synthetic ones that we've seen in the previous slides, genetic. And again, redox behavior was studied and they found very good results. So and this process was used as a commercial bioanode in bioelectrophoton process for degradation of organic pollutants such as textile dyes. So I would just like to conclude by saying that it's a very, 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 very exciting area of enzyme mobilization. A lot of research has been done, but more research needs to be conducted on resource-efficient approaches to minimize material and energy consumption and reduce waste. And there is a possibility that these immobilized enzyme biocatalyst systems can lead to transformational new technologies for chemical industry, and textiles with these biocatalysts can in future provide a totally new class of technical textiles with widespread applications outside the textile domain in prospects such as pharmaceuticals, chemistry, and biochemistry. Thank you.
Thank you, Professor Gupta. We have a few questions. Probably we can address them in the next few minutes or so. Whether the enzyme treatment is more effective in natural fiber rather than on synthetics?
So it's not true. I mean, it's a different system. So like I showed you some examples, it is possible to do it on polyester, on nylon, on carbon fiber. So it's what system you choose. So there is no this thing as it is more effective on, it can be done on any fiber.
Okay.
So yeah.
And how to select a particular immobilization technique based on substrate and enzyme?
Yeah, so I think some of the examples that I showed you were with that specific purpose in mind to demonstrate that every time, I think you have to have the end purpose in mind first. What do you want to use the enzyme for? So first you will use the right enzyme that you need. What is the reaction that you want to catalyze? Based on that, you will choose the enzyme, and then the substrate is really incidental in this case. So you can use any. You can use natural. You can use synthetic, and then the right cross-linking agent will have to be used, or the techniques will have to be used. So it is a very system-specific thing, but it is possible to do it with all type of substrates. Can be any. Enzymes, only some can be immobilized, not all.
Okay. Does enzyme modification has effect on enzyme specificity and activity?
Not on enzyme specificity. That's the whole USP of enzymes. But activity, of course, goes down. They go down by 50, 60, 70% as of now. So that's one area of research how can we immobilize and still get higher efficiency? So effectiveness goes down, but specificity is not important. Yeah.
Sure. And how about stability of the textile, such as cotton, in the reaction system to which immobilized enzyme is used, considering repeat use?
Yeah, so good question. So that will have to be seen. If you are going to, we know that a lot of, so we know what are the kind of behavior of our textiles. We know cotton is biodegradable. If you put it in a reactor, aqueous reactor, over a period of time, it's going to degrade. So that choice will have to be made as to where do we want to use it, and keeping the inherent behavior of the fiber in mind, I think we'll have to choose the application. And also because this is not an endless thing. When you're using it in a reactor, there will be a number of times when you can use it. So maybe you can use it 20 times, maybe you can use it 50 times. So we only need to see whether the material maintains its integrity for that number of uses. And after that, you have to change. So that's the advantage, where instead of using, electrodes like gold and platinum, which is so expensive and so difficult to replace, this is really, the cost is a big factor, big beneficial factor in this.
Yeah. Thank you, Professor Gupta. There are lots of questions popping up. Unfortunately, we already exceeded the time allocated to us.
I'm sorry, I did not
So
realize that.
I need to draw it to conclusion. Thank you very much for your excellent talk.
Thank you.
Okay, Dr. Ganesh,
Sir?
you can close the section now.
Yes, sir. Can you conclude that, sir? Followed that, I will give the thanks. Prasad, sir. Sir, can you conclude, sir?
Oh, okay. Sorry, I thought you want to conclude.
Yeah, I think this is Neelakrishnan. Dr. Prasad, if you can just conclude the session, I think Ganeshan and I will kind of hand it over to the next session, I guess.
Okay, thank you, Dr. Neelakrishnan. We had two excellent talks from IIT Delhi, and both distinguished professors in their specific areas. Very, very interesting talks. One covers the chemistry area, another covers the fabric manufacturing technologies. And Professor Kothari had many, many decades of experience. And what Professor Gupta is developing and talking about are very relevant for today: sustainability, natural materials, circular economy. These are all the buzzwords now, and no doubt we'll be moving away from disposable nonwovens to more sustainable materials into the future. And it's both excellent talks today. Thank you very much.
Thank you, sir. So on behalf of PSG College of Technology, Textile and Automobile Department, we will sincerely give a thanks to Deepthi ma'am and VK Kothari sir to deliver a nice presentation. Also, we can give extend warm heartfelt thanks to Dr. Professor Prasad Poturi for session the chair. Thank you, sir.
Thank you, Professors Kothari, Deepthi Gupta, and thank you for chairing the session, sir. Dr. Prasad and Dr. Ganeshan. I think we'll take a break now, and Ganeshan, we normally give about 15 minutes.
10 minutes break, sir, then we can talk.
You're very strict. Okay, we'll take 10-minute break and then we'll reassemble, I think, at the different link, I guess.
Yes, sir. It's a different link.
All right. Thank you very much. Thank you.
Thank you.
Thank you.